Welcome back. We'll continue with our development of the finite element equations. At the end of the last segment, we got as far as looking at the individual integrals in the finite dimensional weak form, the Galerkin weak form, and writing them out as matrix vector products. Okay, this is where we're going to pick up today. The topic of this segment, at least, is going to be the finite element equations in matrix vector form. Okay. Now, what I'd like to do here is perhaps just recall the forms of the integrals. Okay? So, we saw that when we put everything together, we had, for this integral over omega wh comma x sigma h a dx, we had the following. We had a row vector of degrees of freedom corresponding to the weighting function, and this began with this particular entry, right? C2, C3 in terms of global degree of freedom numbers, right? This went all the way until we came to C, NEL plus 1. Okay? This was multiplied by EA. And then we had this matrix, which I'm going to try to write out really neatly today. So, if I recall correctly, in this position we had minus 1 over h1. In the next we have 1 over h1 plus 1 over h2. And here we ought to have had minus 1 over h2. In this position we have minus 1 over h2. And here we have 1 over h2 plus 1 over h3. Here we have minus 1 over h3, minus 1 over h3. Here we have 1 over h3 plus other terms, and I'll stop because if not I won't have a suitable point to stop. Okay. This continues all the way down until we have in the very last position here, okay, the very last little sub-matrix, sub 2 by 2 matrix. We have 1 over h n e l minus 1, 1 plus 1 over h n e l minus 1 over h NEL, and here finally we have 1 over h NEL minus 1 over h NEL. Okay, and this matrix is closed here, and okay, I'm going to multiply this by a row vector, okay, and because I've run out of room there, I'm going to write the row vector down here, sorry, the column vector down here. This column vector has global degrees of freedom 1, 2, all the way down to D, N, E, L plus 1. Okay, and let's just recall that this goes up here. Okay. This is what we had for our integral on the left hand side. All right. For the integral on the right hand side, which as you will recall comes from the force, we had the following. The integral itself was integral over omega WH F A dx. And this, when all was said and done, also was multiplied by the same c vector, up to c n e l plus 1, and multiplying it here was f a, and let me see, I think I had an f a perhaps over 2, and the contributions here were the following. We had in the very first position, we had H1 plus H2. The next position we had H2 plus H2 plus H3, and so on, up to, in the very last two positions, we had H NEL minus 1 plus H NEL, and finally here we had H NEL. Okay. All right, we had this, and then we had the very last term, which was an easy one to write. The last term was WH evaluated at L T A, and this, following the same convention that we've adopted for the other terms, was multiplied by the vector of c degrees of freedom, which properly is the weighting function degrees of freedom, going all the way up to c NEL plus 1, and the vector that it was, that row vector is multiplying, the column vector here, was filled with zeros all the way up to the very last entry, and in the very last entry we had TA. Okay, and I realize now that for all the h's here, for all the element lengths, I'd used superscripts up to now, but the first two slides of this segment I've been using subscripts. We'll go back to superscripts, but let me just put in a remark here so that if you review these notes, you will, if you review these lectures, you will note that as well. We're using H sub E here instead of H sup E, and we're now going to go back to H sup E, okay, on what follows in the next slide. Okay, so we have these terms here, and what we want to do now is to begin assembling them. As a first step, what I'm going to do is just to get a little more insight and to make it a little less unwieldy, I am going to say that we are going to consider the case where all the element lengths are the same. The development so far, and especially the form we have on the previous slide and this one, and what we've done in the previous segments, should convince you that the method is completely applicable to formulations where, or to meshes where the elements do not have the same lengths. Just for some sort of brevity in writing and convenience and some amount of insight as well, I'm going to say all the HEs are the same. Okay, so let me just make this remark also here. Consider HE constant for all E. Okay, so there's a single HE. We don't need to distinguish H1, H2, and so on. All right, just makes things a little easier to write. Okay, so now if we go back and look at the matrices we've put together, what you will observe, or what we should observe, is something about the sizes of these matrices. Okay, so we'll do this, but now we're going to use common element lengths. Okay, note. Okay, note that the finite dimensional weak form that we have with all these matrix vector expressions is essentially this: C2, C3, the CNEL plus 1 times EA. Now, because we have a common element length, just for convenience, I'm going to pull it out. Okay, and this is what I wanted to achieve as well. Okay, this now multiplying the matrix, which has the form -1, 2, -1, -1, 2, -1, and so on. Okay, until we come all the way down here to 2, -1, -1, -1, 1. Okay, all of this now multiplying the displacement degrees of freedom if we're doing an elasticity problem, or more generally, the solution degrees of freedom, right? The trial solution degrees of freedom. Okay, this is our entire left-hand side of the weak form. Equal to, on the right-hand side, we have C2, C3, CNEL plus 1, F, A, H over 2. And now, again, because all the H's are the same, we have here 2, 2, all the way down until we have a 1 in the final entry. Okay, plus C2, C3, CNEL plus 1, multiplying zeros everywhere in this column vector until we come down to TA. Okay, so for the special case of a mesh where all the elements have the same length, HE, we have this nice simple representation, right? And that's an HE there as well. Okay, what I'd like to do here now is just pay some attention to the sizes of the relevant vectors and matrices. Should be completely clear, of course, it's pretty much written here the way we've written out this vector, this row vector, that this row vector has dimensions NEL, right? It's of length NEL, right? Simply because it's going from 2 to NEL plus 1, right? This column vector here is NEL plus 1, which leads us to conclude that this matrix is of dimension NEL cross NEL plus 1. Okay, essentially the same thing on the right hand side tells us that this column vector as well as that one are of length NEL, and of course this is the same, the C vector is the same one, right? Right, so both of these are of length NEL, right? Obviously, just for consistency of the matrix vector products. Now, so we have this form, and let's see what else we know about it. Can you recognize what we know about one of the degrees of freedom in the vector of nodal trial solution values? So look at that vector, the D vector, carefully, and think of what we know about at least one of those degrees of freedom, and in fact one of those degrees of freedom. Because of the Kronecker delta property of our basis functions, we've demonstrated that this particular entry, right, is actually U0, U0, right? And that comes about because you remember what our mesh looks like. Right, so this is element 1, and this position here is x, this node is x1 equals 0, right? And on that node, the degree of freedom is d1, right, which is u0, okay, which is a known, right, because it's the Dirichlet boundary condition, right? What this tells us is that when we look at the matrix vector product on the left-hand side of this matrix vector equation, we can actually take this entire column, right, and I'm going to do something which is a little not strictly legal, but I'm going to draw out that column vector, right? And because of the nature of this matrix, okay, the other entries in this column vector are 0, right, all the way down. Okay. All right. Essentially, what we can do now is, because we know d1 equals u0, right, and we recognize that this particular column vector that I've marked out in the matrix is the one containing matrix elements that multiply d1, which is equal to u0, which is known. We are at liberty to actually move it to the right-hand side. Okay? All right. So what we will do here is, okay, is the following. We are going to now write this as C2, C3, CNEL plus 1 EA over HE times the matrix now that is considerably simplified, well, not considerably, but at least somewhat simplified. 2 minus 1, minus 1, 2, minus 1, going all the way down to minus 1, 2, minus 1, minus 1, 1. Okay, and the diagonal is this one, and the upper and lower diagonals are those ones. Okay, this thing multiplying the vector now d2, d3, all the way down to d n e l plus 1, right, equals C2, C3 up to CNEL plus 1. Now multiplying, I'm going to put all the column vectors together here. Okay, the first column vector is FAHE over 2, multiplying 2's all the way down except for the very last element, which is 1. Plus another column vector filled with zeros all the way down to the very last entry, which is t times a. And now there is a newcomer to the party here, right? The column vector that we looked at here, and I'll draw yet another arrow to it, can be moved to the right-hand side. Recognizing that we have a minus 1 in this entry, okay, we have on the right-hand side EA over HE multiplying D1, but D1 is known, right? D1 is known to be equal to U0 because of two things, because of the Dirichlet boundary condition as well as the Kronecker delta property of our basis functions. Okay. Now, when we look at the size of our matrices, we recognize that really this is the only one that we need to correct, right? Because it's lost a column, right? Earlier it had NEL rows and NEL plus 1 columns, right? It has now lost a column. Okay. So, and we are going to recognize, therefore, that it is a matrix of size NEL cross NEL. Okay, and we're going to do one more thing. We are going to call this, so NEL cross NEL is the dimension, or are the dimensions of this matrix, and we are going to write this as the matrix K. All right. Likewise, for obvious reasons, we are going to regard this vector of degrees of freedom for the weighting function as the vector C. Since all our vectors are, we like to think of vectors as being column vectors, and recognizing that we've written this as a row vector, I'm going to call it C transpose. Okay, the idea being that a vector is terminology that we reserve for column vectors. All right. Likewise, this vector, again for obvious reasons, is going to be my D vector. Okay, here again we have our C vector, and now I'm going to look at all of this, right, all of these contributions together and call them my F vector. Okay, I just recognize that this C vector again is a C transpose, again using this idea of row and column vectors. Okay.